So 2 months ago, I put out a poll asking people what they'd like to see as my next computer project. And the one that took the most interest by quite a large margin was a new computer project with a clock that is as fast as I can possibly manage. Now, that one is rather interesting because I had been thinking of doing something like that for a while now. And that's mainly because a lot of the computers that I build tend to have a fairly slow clock. I think the fastest one I've got, I believe, is on the Skittlebits project or the Deep Thought project. I'm not entirely certain which one, but even so, both those computers have a clock cycle of 40 ticks or more, so 4 seconds to complete one clock cycle. It's not really ideal. I think we can do a lot better. So my goal was with this project to actually create a computer with a clock cycle of 10 ticks, meaning 1 second to complete a single clock cycle. Now, getting a computer that is relatively fast isn't too terribly challenging. All you really need to do is just create a pipeline computer. So that was definitely something I could do. Problem is, to me, a normal pipeline computer really, it just isn't that interesting of a project to me, because the way these pipeline computers work is you basically split the execution system into separate stages, and the idea is that each stage would hold a single instruction. With something like this, I think this is 5 stages, you can have up to 5 instructions running at any given time. But they're all very, very simple instructions. They basically equate to what is basically just a move operation. So you can move from register to register, move from register to memory, memory to register, or you can move between 2 registers back to another register through the ALU. Or in the case of jumps and branches and things like that, you can move from the instruction pointer to memory, memory to instruction pointer, register to instruction pointer. But they're all, these by themselves, they can be combined together to create some pretty powerful programs, but ultimately they are all very basic move operations, and they only perform one move operation, and that's the key to making these pipelines work like they do. Now, again, to me, I could do that, but it wasn't really as interesting as I'd like it to be. So one of the requirements, or one of the other requirements I had for this project, was to actually make something that ran a complex instruction set. And so obviously we've got the 5 to 10 ticks. We're probably going to be leaning more towards the 10 ticks, but if we can go faster, great. Running a complex instruction, that's going to be a requirement. I also want interrupt capabilities for this computer system. I think interrupts are actually really cool and very underutilized when it comes to building other computer projects. I don't really see interrupts in most other computers, so that's why I kind of want to explore the idea a little bit. And then optionally, what I'd like is to have the computer throw exceptions, because again, I think exceptions is one of those underutilized things where it's a topic I don't see many people explore, and it's something that I'd be curious about to see if I get that working myself. So we're going to try and go for stack overflow, integer overflow. It's probably not going to happen, but if I can get that in there, that'll be great. And so I gave this a bit of thought, and I think I came up with an instruction set that I think will be a good challenge for me to work on, as well as meet some of these goals and criterias. And that's what I got right here. So if we look over, this is just the sort of the architectural details, what kind of functions, what kind of registers, things like that. We're going to be going for 8 registers. 4 of them are going to be special purpose. The other are going to be general purpose. So that's going to be accumulator and secondary. Arithmetic operations or ALU operations are going to be done between those. We've got a pointer register, which we can use in pointer instructions. We've got a counter register, and that's actually got its own special instruction. We'll get to that in a second. And then the others are just general purpose. You can move things to there if you need to. ALU, we're going for 16 operations, and I picked that specifically because if you look at binary operations, you can usually get about 8 of those. And so I figured, well, why not give it 8 unary operations as well? And that way I can differentiate between binary and unary operations with a single bit. So that's the route that I went with there. As far as branch conditions, we're just going to go with the basics. Equal, less than, greater than, and always. Now with the always flag, we've actually got some interesting functionality associated with this. For example, the always on flag, basically just the uninverted always flag. That's just going to be referred to as the jump instruction. However, the never flag, we're actually going to repurpose that as the halt instruction, and there's a reason why I did that. It's mainly just because it was the best way to squeeze that into the instruction set neatly. So we're just going to have the inverted always flag default to a never or a halt instruction. Now, as far as the flags, again, we're going for some of the basic ones. Carry flag, we're going to try and go for the overflow. Again, that depends if we want to implement exceptions or not. The interrupt mask is going to be, again, for the interrupt capabilities. We're going to want that mask so that we can control when the computer is handling an interrupt and when it's not. As well as a halt flag. Again, that's going to be controlled by the halt instruction, and it's going to be managed by the interrupt instructions as well as the interrupt return instructions. Exception flag, that's kind of an if. I'm not entirely certain. Again, if we decide to have exceptions, we could mask those using this, but then, as for the last three, we got the basics. Greater, equal, than, or less than. Now, as far as other registers and other things are concerned, obviously we've got the flag registers. These are all accessed directly, so we got the flag registers, instruction pointer, stack pointer, base pointer. Basically, the stack pointer and base pointer are going to be used to manage the stack frames, and those will be accessed using the call and return instructions. Then we've also got some ROMs, one being the stack size as well as the stack base. I've got those backwards, stack base and stack size. And those will control where in memory the stack resides. And the idea here is that if the stack pointer ever exceeds these two values, we can use that to throw an exception. And then lastly, you've got a software interrupt vector table. This is just setting where the computer will go if ever it encounters any kind of interrupt, either a hardware or software interrupt. Moving on, we can actually look at the instructions themselves. Now, I rather like the instruction set that I came up with here because for the first time I've actually been able to fully deck out an entire array of 256 instructions. Technically 255 because we do have that no-op there, but honestly I think having a no-op in an instruction set is actually really useful. If your program memory is filled with nothing but zeros, you don't want the computer to just be doing something with those zeros. You want it to basically just sit there. So that's why I typically include a no-op instruction. But the way I've got this split up, since most arguments is 3 bits, that means that any instruction is going to have 8 variants. So what I've done is I basically just split this down the middle, with each half being a consecutive chunk of 8 instructions. And then I just kind of slotted each set of instructions where it seems like it'd fit most logically, with all the random odds and ends instructions being in the first 8 here. So obviously we've got the no-op, we've got push all and pop all. Now again, I wanted to go for a complex instruction set, so these instructions are actually going to take all 8 registers and either push them to the stack or pop them to the stack, which is going to require multiple move operations, which means it's likely going to require multiple clock cycles. Then we've got the call and return instruction as well as the interrupt return instruction. That's just for returning out of an interrupt handler. And then we've got these instructions here, the AND flag immediate and OR flag immediate. Those will, as it says on the tin, take an immediate 8-bit argument and either AND it with the flag register or OR it with the flag register. And this basically acts as a set and reset instruction. Then we've got the load immediate instructions. These take a 16-bit argument and load that value directly into one of the registers. And I am going with a 16-bit architecture just because I think it'll probably be a little bit more interesting than just your run-of-the-mill 8-bit CPU. Obviously, there's not too terribly much when it comes to the differences between 8-bit and 16-bit architectures. All you're doing is just expanding the bus, but still, I think having a 16-bit computer would be cool here. Then we've got move. Now, I'm going with more of an Intel-style move operation where one register acts as a constant source or destination, and the other argument is the only one that's variable. So you'll see here we can move from A to A, move from S to A, move from W to A, move from X to A. Basically, we're moving from any instruction or any register to the A register, and then over here is the reciprocal instruction from the A register to one of the other registers. Then we've got store and load. These basically take any register and store it into memory or retrieve it from memory. Then we've got indirect store and load. These are basically the same thing as store and load, except it uses the pointer register to point to memory as opposed to using a constant address argument. Push and pop, these basically just, as it says on the tin, just push the values of the registers or pop the values of these registers to or from the stack. Then we've got store local and load local. These are for local variables that would be stored on the stack. I wanted a nice clean way of actually accessing local variables when it came to those sorts of things because, again, I want to support proper stack frames on this computer. But the problem is if I were to access local variables by using the base pointer plus an offset, personally that doesn't really make much, I mean, it makes sense, but I don't like how clunky it is. There's a lot of mental things that you've got to keep track of in order to make sure that you're grabbing the right local variables. So I wanted a proper instruction for that. And instead of using a base pointer plus offset, it just uses an index. So if I were to say store local A add argument 2, that's going to take the contents of the A register and store it in the local variable number 2, which could be the base pointer minus 3 or 4. It doesn't really matter. It's abstracted away. It's the point there. Then we've got the branches, branch of equal, not equal. These are basically just your flags. Then we've got that jump and halt instruction that I mentioned earlier, as well as the software interrupts. We've got 8 of those. Now here we can see the immediate operation instructions. These are basically just all binary operations that are performed on the A register along with an immediate value. And then here we've got another special instruction that I really wanted to add. This is count and branch if not equal. And what that does is it basically just increments the value in the counter register, the C register, and then compares it to whatever register is provided by the argument, A, S, W, X, Y, Z, so on and so forth. If they are not equal, it branches. And what this allows me to do then is in one instruction set up basically a for loop. So if I set the A register, or I guess any other register, if I set the W register equal to 5, and then set the C register to 0, I can run some code, run this instruction. It will automatically increment the C counter, compare it to the W register, and if they are not equal, it will branch and loop again. And then the later 128 instructions here, these are basically just your quintessential ALU operations. So we can perform add, subtract, add plus carry, sub plus carry between the A register and another register. And so the first 64 instructions here, these are all the binary operations that you can perform. The next 64, these are all the unary operations. And so now we get to this document here. This is basically just a table that shows the groups of instructions, what their opcodes are, what their arguments are, and what it is they actually do. And this is actually helpful here because it actually shows exactly how much variability I have with each of these instructions. So with a pipeline computer, your instructions have to remain a fixed width. You can't vary the length of the instruction any. If your longest instruction is 24 bits wide, all of your instructions have to be 24 bits wide. Otherwise, you can't access each instruction in one clock cycle. I don't really like doing that. I think having 24 bits allocated to an instruction that only needs 8 is kind of a waste of space. So mine is 8-bit aligned, but they can vary in length from 1 byte to 3 bytes, basically. So you can see a couple different 1-byte instructions. Some of them have 3 bytes. In this case, like the call instruction, it's going to have a high byte and low byte argument since we're dealing with 16-bit values here. And then some of them only have 1 additional byte for the argument, such as that and or flag immediate instructions. Those only need another 8 bits. So for that reason, these instructions are only 16 bits wide. Same thing with the microcode sequences. Again, with a standard pipeline computer, your instructions are only going to ever be 1 move operation in length at any time. Granted, it'll probably take 5 clock cycles to execute if you have a 5-stage pipeline CPU, but even still, it is 1 move operation. Here you can see that I've got instructions that can be a 1 move operation, but then we've got others that are definitely more than just 1 move. So for that reason, you can see that the instruction length varies from 1 to 3 bytes. The microcode sequence, basically the number of microcodes we're executing, that can vary drastically. And as a result, this is a much more, I would say, interesting instruction set to try and implement. So how exactly do I intend on implementing this sort of thing? Well, as it stands with executing microcodes, that's going to be pretty straightforward. We can just use a standard pipeline model for that. The trick then will be generating the microcodes themselves. What I'm basically going for is a model similar to what I had with the FatStacks project, although it's going to have several improvements that I think the FatStacks project would have benefited from if I had figured these things out sooner. But basically what we're going to have is the first two stages, the fetch and decode. Those are going to be what's responsible for fetching the instructions and then generating these microcode sequences, which then can then be pushed to the rest of the pipeline stage and then executed like a normal pipeline computer. So the rest of the computer, the execute stage, the memory access stage, the write back, all that stuff is going to be pretty bog standard when it comes to just a general pipeline design. The decode stage, like I said, that's going to be what actually generates these microcode sequences. That's pretty straightforward. It's likely just going to be a state machine that takes the instruction from the fetch stage and produces a microcode sequence, and then when it's done, goes back to the fetch stage and requests the next instruction. It's the fetch stage that's going to be the most interesting because, again, we have 8-bit memory that's going to contain instructions that can be 8, 16, or 24 bits wide. And so to actually fetch these instructions and get them ready for the decode stage will require a little bit of interesting logic. Not only that, but there are some instructions that can be executed entirely within the fetch stage, that being things like call or jump, so long as it's a non-conditional branch instruction of that sort. You could actually execute that entirely within the fetch stage. You wouldn't have to send anything downstream and figure any of that stuff out. But then when it comes to instructions that have a dependency, such as return, or branch instructions that require a condition to be settled, that's where the logic's going to be a little bit interesting. And so that gives us sort of a chicken and eggs type situation, where I need the fetch stage to actually be fully designed and fully built before I can actually start designing the rest of the pipeline. But I need the rest of the pipeline in order to actually figure out how to build the fetch stage. So at this point in time, I'm disregarding branching, I'm disregarding dependencies, I'm disregarding all of those, and all I'm doing is I'm just building a basic fetch stage for the time being that can take in a stream of 8-bit information, basically 1 byte at a time, and produce a 24-bit opcode output that the next stage can then use. Now, on paper, that doesn't sound too terribly complex because all you really have to do is just bring in the value from program memory and then latch it to whatever output it needs to go on. If it's just a 1-byte instruction, just latch the opcode output. 2 bytes, opcode and high byte. 3 bytes, opcode, high byte, and low byte. Fairly straightforward. Thing is, though, if we have a 3-byte instruction and we have the decode stage that's requesting that next instruction, we have to wait 3 clock cycles for that instruction to be ready. Now, we can actually cheese it a little bit in the fact that if we just send off the decode stage when we have the opcode byte, we really only need to wait 1 clock cycle because the decode stage only needs the opcode. It's the rest of the stages that needs the high byte and low byte, and we can get those fetched by the time they're actually needed. That's not too terribly difficult, but here's the thing, is if we have 1 3-byte instruction after another, well, then we end up having to wait. We have to fetch the last 2 bytes of the first instruction before we can fetch the next one. And that's not an unreasonable possibility. It is quite feasible for something like that to happen. If we have something like this, where it's only 1 microcode that's being executed, but 3 bytes to actually fetch, if we have 2 of those, one after the other, the decode stage is going to request the next instruction pretty much 1 clock cycle later, but we won't be able to actually have that ready because we still need to fetch the last 2 bytes of the previous instruction. So to solve this, I actually want to have a small instruction queue inside the fetch stage here. The idea being that as the decode stage is busy producing opcodes, if it's not requesting an instruction, we're still fetching instructions and we're queuing them up. That way, the next time the decode stage requests an instruction, whether it's a 1-byte, 2-byte, or 3-byte instruction, we can provide that immediately. Now, that is a little bit of a challenge because now that we're dealing with we're dealing with queues, we need a means of making sure that they remain synchronized, because obviously when we bring data in 8 bits at a time, 1 byte at a time, we're only writing to 1 queue at a time, which means there's a chance that these can actually become out of sync. And when we actually want to request data, when we pop values off of that queue, we don't want part of one instruction and then a part of another instruction all on the same output. We want the same instruction to come out at the same time. And so what I've done to actually address this issue here is the fetch stage will actually do a little bit of decoding itself. Not too terribly much. It just needs to determine if the instruction is 1 byte in length, 2 bytes, or 3 bytes. And if it's 1 byte in length, it'll actually take that same byte and push it to all 3 of the queues. And the reason why is, even though the high byte and low byte values of the instruction bus won't actually be used, it still needs something there to keep the queues synchronized. So the same value gets pushed to all 3 of them, and that just means that the high byte and low byte queues just have a redundant copy of the opcode. Same thing with a 2 byte instruction. We first take the first byte, we push it to the opcode queue. Then the next byte gets pushed to both the high byte and low byte. At that point, it doesn't really matter what part of the bus we use. We can use both, technically. But if it's just the high byte that we use, it'll be there regardless. And then the same thing with the 3 byte instruction. We take the first one, we push it to the opcode queue. Second one goes to the high byte. Third one goes to the low byte. Basically, doing it this way ensures that there will always be something that gets pushed to all 3 queues at any given time. And then, as a result, anytime we pop those values off of the queue, we will get the instruction and all of its constituent parts. Even if it's just garbage information, it'll all still be there. Now, as far as synchronizing the instructions between the fetch stage and the decode stage, there's 2 pins that's responsible for that. That's going to be the instruction request pin and the instruction acknowledge pin. The instruction request pin is going to be updated on the rising edge of the clock, and that's going to remain on if the decode stage wants an instruction, and it's going to turn off if the decode stage is currently in the process of executing an instruction. So if the instruction it receives is only 1 clock cycle long, it's going to keep that request signal on because it knows in the next clock cycle it's going to require an instruction. However, if it knows that in the next clock cycle it's going to still be executing the current instruction, it'll just turn that off. Acknowledge, on the other hand, that gets updated on the falling edge, and that indicates when the instruction is actually available. Now, determining the status of the acknowledge bit is actually fairly straightforward, because all we really need to do is just sample the empty flag of the opcode queue, and if it is not empty, we've got something available. That does mean that there's a possibility that we could have something in the opcode queue and nothing in the data queues, and that you would think might cause a bit of a synchronization error. Not necessarily, because what will happen is the queues will then be updated as if it had something in them, which means it'll just be pointing to garbage, but then as the fetch stage continues to execute, it will replace that garbage with actual useful information. And so putting it all together, this is basically what I came up with to actually implement these behavioral requirements. Again, I know that the behavior isn't completely fleshed out, but we need the fetch stage in order to design the rest of the instruction queue, or the pipeline. And we need the pipeline in order to finish designing the fetch stage. So we're just going to be starting with this as sort of a prototype. I'm going to use this to build the rest of the computer, and then we'll update the design as we need it. But it's fairly straightforward. We've got a clock, and that clock can be disabled by the full pin of the opcode queue. So if the opcode queue is full, that's going to disable quite a lot of things, one of them being the clock actually going to the counter register. Counter register just serves as your standard instruction pointer, goes to the program memory returns data, and that data can go to one of the 3 queues. And which one it goes to is determined by the state machine here, which takes its input from this decoder here. Now this decoder just takes the instruction and just determines if it requires an additional byte or an additional 2 bytes, and that's what this F2 and F3 bits are for. These are abbreviation for fetch 2 bytes and fetch 3 bytes. If neither one of these is on, the state machine will latch all 3 queues. If F2 is on, it'll latch the opcode queue, and then on the next clock cycle, when we have the next byte, it'll latch the high byte and low byte. And if we have an F3 signal, it'll latch the opcode queue first, on the next clock cycle the high byte, and then the clock cycle after that the low byte. Again, if the opcode queue is full, it's going to disable writing to itself as well as writing to the high byte and low byte. Actually, this needs to be updated, and I still haven't updated that. This is something I found last week. We don't actually want to disable writing to the high byte or low byte if the opcode queue is full. And the reason why is because if these instructions, or if these queues are 1 byte away from being full, if we bring in a 3-byte instruction, that's going to go to the opcode queue, that's going to fill up, but these other two still have 1 spot left, and we still have 2 bytes to actually fetch. So for that reason, this shouldn't actually affect these two. I just haven't updated the schematics. So just ignore those for now. Basically, like I said, full signal is going to disable that. It's going to disable the state machine. And that state machine is going to only consider that when it's in state S1, because if it's in state 2 or 3, where it's actually writing to the other two queues, we don't want it to stop during that process. If it's in the middle of fetching more bytes, we want to complete that before going back to the first state and then waiting. Now for the queue design, I've tried a couple different queue designs before. I first tried the systolic array queue, and the reason why is because I figured that one might be promising in the fact that writing to it can be done fairly quickly. Because the write and read sides are completely independent, I shouldn't have to rely too much on the clock to actually synchronize those things. Problem was, with the systolic queues, there just was no way of making each stage small enough in terms of time to get the information from one end of the queue to the other fast enough. So if I wanted a queue of 5 bytes in length, it would have taken about 14 ticks to actually get the data from one side to the other. So 14 or 15 ticks, that's too long. I don't have that time. So the next one I tried is actually this one right here. And again, I need to update these documents. But the next one I tried was the circular buffer queue. And that's your bog standard queue system. You basically just have 2 pointer registers, and that controls where you read from and write to in memory. That sort of worked, but I couldn't get the memory access fast enough. That was the biggest issue I was having. So what I ended up going with eventually was just a shift register queue design. And this was a shift register design that I found on the OR server, designed by Great Gamer. And it's not terribly great. It does have a few disadvantages. It's the fastest I could get to it as far as latency was concerned was a 5-tick delay, which is just barely enough, but honestly, I think we could have done better. But for the time being, it's good enough. It works, so we're just going to move on with it. And then actually generating the instruction request and instruction acknowledge signals. Obviously, the instruction request is going to be handled by the decoder, but there is some timing requirements. You'll actually see in the prototype I built, I have a circuit that manages that signal just to synchronize it with the clock. The idea here is that so long as the queue is empty and on the falling edge of the clock, if this signal is present, it's going to advance the queues. And if it's able to advance the queues successfully, it's going to set the instruction acknowledge pin, which on the falling edge of the clock, it's going to reset that. So that's the theory anyway. Now, using that information, I've gone ahead and I built a prototype here. Biggest thing you're going to notice here is it is vertical, which is definitely new to me. I've seen a lot of different computer designs out there, and it seems like all the fast ones use vertical wiring and vertical redstone. This stuff definitely seems to be quite a lot faster than horizontal redstone. Not entirely certain about diagonal, but, one step at a time. So vertical redstone is what I'm going for. There's a lot of great components on the OR server that I've nabbed and used, and as well as some components of my own design. I've already gotten fleck for this. This is my state machine. But I'll be honest here, there isn't really a good way to take the output of the decoder and connect it to outputs that line up with the input of itself. So that's the reason for the pistons here. Like I said, apparently pistons and vertical redstone aren't supposed to mix, but here I am using them, so oh well. But here we've got the program memory, and I really like this because I believe this is 32 bytes in a very compact form. The latency of this thing is extremely low. There's only 2 ticks of delay between the output and the furthest point there. So 32 bytes with only 2 ticks of delay, I'd say that's pretty impressive. Then we've got the central bus, which just goes to the 3 queue designs. These are, again, the queues by Great Gamer. As well as the decoder here, which just determines if we need to fetch additional bytes, and the state machine that controls the writing to each queue. Over here, we've got a decoder that actually controls the ROM as well as the program counter. Just a basic vertical register with an incrementer circuit. Not anything too terribly spectacular. I literally just threw this together for the sake of testing. And then over here, we can see the instruction acknowledge and instruction request lines. And then this is the circuit that I've put together to synchronize the instruction request signal. So that's what that's for. It's not actually part of the design. This is just something that I'm using to make sure that this signal lines up as far as time is concerned as it should. Now, Redstone, when put together, obviously it does look pretty impressive. And, you know, I won't lie, I am actually quite proud of how this turned out. But the biggest question that I think we should be asking is, does this actually work? To figure that out, or to determine that, I've got a basic quote-unquote program loaded in the program memory here. This isn't anything special. It's literally just testing whether or not this thing can determine how many bytes it needs to fetch and where it puts it in the queue. So as a result, the instructions we got loaded on here is the first one is 01, which is push all. That's a 1 byte instruction. Then we've got 06AA. That's going to be and flag immediate with the argument being AA. That's a 2 byte instruction. Then we have got, let's see here, 0333CC. That's a 3 byte instruction. That's going to be a call instruction with a 16-bit argument. And then everything after that is just single byte instructions, just software interrupts, so 0x, 68, 69, and 6A. And so the idea here is that if I run this, we should see when we request the first instruction, we should see 010101 across the board. Next one, we should see 06AAAA. Then we should see 0333CC. And then again, because the rest of them is just single byte instructions, we should see repeating patterns like that. So that's the idea here. Let's go ahead and run this. Just start the clock. And we can actually see that we've already exceeded the first instruction, or the first byte being loaded. We're already on the 3rd now. Once that signal gets down to here, the instruction queues are full, and we can start requesting. We can actually start requesting anytime, but I just like to let it fill up. But if we go ahead and flip this, on the next rising edge of the clock, we'll get a request signal. And there we can see the first instruction, 010101. If we request another instruction, there we go. The next one should be 06AAAA, so that's 06AAAA. Good. Just had to double check. I thought the lamp was off for a second there. We'll request another instruction here. And the last one should be 0333CC. So there's 0333CC. So yeah, it does work pretty well. It can fetch instructions of varying lengths and put them in the appropriate queues. The queues remain nice and synchronized, and everything seems to be working. There shouldn't be any problems, right? Well, there is one issue, and that's the fact that it is nowhere near its target clock speed. This is running at 44 ticks, or 4.4 seconds per clock cycle, which is significantly slower than what I was aiming for. So obviously, despite my efforts to try and optimize everything, I tried to make sure everything had the shortest path, I was using the fastest components, it's still pretty slow. So there's going to be some changes that's going to need to be made before I can actually move on. Possibly, maybe. We could be dealing with a situation of premature optimization, in that maybe we're trying to speed this up before we actually know that this is the design we want to go for. That's entirely possible. So there's really 2 ways we could go about this. One is we could start developing the rest of the computer with just this slow clock cycle and then optimize everything for speed. Or we can try and optimize this for speed and then design the rest of the computer. I'm inclined to design the rest of the computer because, again, this is just a prototype. But if I were to optimize it for speed, there's a couple things that I might do. The first is I could split this into 2 stages instead of just one. One being where I actually just fetch the instructions, and the other where I just sort it into their appropriate queues. The other thing that I could probably do to increase this is actually change the decoder design. Right now, it's doing the bog standard register output goes to decoder, goes to inputs of the ROM, goes to outputs. What I could do instead is I could actually set this up where this is the counter. So we could have some kind of circuit here that turns this torch on, then this one, then this one, then this one, back and forth it goes. And if we need to jump to a different register, we could have or a different address. We could have the register control a decoder. We can then have a circuit that takes the output of the decoder and loads it into this circuit. I think that would be faster. I don't know how much, though. All in all, though, like I said, if we were to go for optimization, we could go down the route. For the time being, I think what I'm going to do is I'm just going to use this as it is to design the rest of the pipeline and just see how that goes. I know that's going to be a little disappointing because the whole point of this project is to try and make a fast computer, but honestly, I mean, this is how designing these things works. So, but yeah, that's the project so far. Like I said, there's not too terribly much, but I think for what I've got here, I think this is actually a pretty good start. So, again, going forward from here, we're probably going to have to start looking into actually building the rest of the pipeline stages, which shouldn't be too terribly difficult. Like I said, the decode stage is just going to be some kind of a state machine, and the rest is just your bog standard pipeline computer. So that shouldn't be too terribly difficult to figure out. But once I get that, then we can start looking back at this fetch stage and see if we can implement some more complicated logic here. Until then, though, that is all I've got to share for now, so thanks for watching. I'd like to take a moment now to thank the people who chose to support my channel on Patreon. Your continued support of my channel is ever appreciated. If you'd like to support my channel, you can do so by going to my Patreon, the link will be in the description, and you can join for as little as $1, which will get you access to the Patreon feed, where I post weekly videos posting about things such as build vlogs and design decisions regarding current projects. Thank you kindly for your consideration, and I will see you in the next video.